Alkynes are kind of like alkanes, but an alkyne has a triple bond. So if you have a triple bond, then somewhere in the molecule, you're going to have a lot different reactivity than if you had just single bonds. Alkynes are much more reactive than alkanes, so it's a good thing to know. The formula for alkynes, CnH2n minus 2, which is kind of a strange thing. So in the example right there, we have an example of a pentyne. Pentyne means 5 carbons, like pentyl. So Cn, N is 5. Number of hydrogens, 5 times 2 minus 8. There's only going to be 8 hydrogens in that formula. And if you look up, that's the case. The triple bond takes out a lot of the hydrogens. Remember, all of these compounds are carbon-based, so they're going to have 4 bonds total, no more. If some of the bonds are taken up by a triple bond, you kick out hydrogens, etc., etc. Pretty good. It's 2-pentyne because if you count left to right, 1, 2, 3, 4, 5. So in this compound, you want to use smallest numbers possible. The 2 represents where the triple bond starts, and that's important. So 2-pentyne. If you counted right to left, this would be 1, 2, 3. You could also call this 3-pentyne, but again, smallest number, longest chain, the big thing, 2-pentyne is better, so you wouldn't use that numbering system. Ethyne is the simplest of the alkynes. Ethyne is 2 carbons because ethyl has 2 carbons. And if you have a triple bond between it, that makes HCCH, where there's a triple bond between the carbons. Ethyne's common name is acetylene. And acetylene torches are what they use for welding. Acetylene is basically an alkyne. A lot of energy in that triple bond that can be broken apart when you weld. An alkene is different than an alkyne. And I want to just put this on pause for a second. Alkanes were the simplest ones, where all the carbons had just hydrogens around, no double bonds, triple bonds, oxygen, etc., etc. Alkynes had a triple bond between them, so that was different, and this is an alkene. Alkenes have a double bond between them, all right? So there's alkanes, alkenes, and alkynes, and hopefully you can see now why the first term of organic chemistry, whoa, I was snowed in because I thought, oh, an alkane and an alkene are the same thing. No, they aren't, as I found out. My grade wasn't exactly the best for that class, but anyway, I digress. No reason to talk about the past, and you will be stronger now because you're hearing this. But anyway, alkenes have a double bond, and so because these are all carbons with 4 bonds total, each of those carbons can be connected to 2 other things, all right? Now, if you look at this first example, there are 1, 2, 3, 4, 5 carbons. So it would be pentane if it was an alkane, but this is not. It has a double bond, so it becomes pentene. The double bond starts between the second and third carbons, so 2-pentene would be fine. We'll talk about trans here in a little bit. However, just like with the alcohols, there is a move to, instead of calling it a 2-pentene, people are now referring it more and more as pent-2-ene. And again, there's some real good reasons why this is the case. I would be happy if you called this trans-2-pentene, but I'm trying to adjust my notes as much as possible to the newer way, so trans-pent-2-ene would be really cool. So anyway, 2 ways to name, 1 way is winning at the other one. Now, the structure that's rotating down there, the double bond you can see is kind of in the middle. And notice how the 2 hydrogens on the opposite sides of the double bond, like one is up and one is down. And that has to do with the trans part that's in front of it. So sometimes when you have an alkene, you're going to see different names there, which help the chemist to know what kind of a compound it is. let's go back to this question and think about which of the following could be an alkene. Now, the generic formula for an alkene, CnH2n. So anything in that list with n carbons and 2 times n hydrogens could be an alkene. So we've already been through a lot of these before, but if you look at that list, the first one and the second one have a CnH2n formula. So like for the first one, n is 2, so 2 times 2 would be 4 hydrogens. Number 2, 5 carbons, 2 times 5, 10 hydrogens. Both of those could be alkenes. So for an alkene, both answers 1 and 2 could be an alkene. Now, if you remember from earlier, we also saw that a cycloalkane also has the generic formula CnH2n. Now, for C2H4, you can't make a cycloalkane. We talked about how you have to have at least 3 carbons to make the cycloalkane. However, it could be an alkene. You could have just a double bond between those 2 carbons and be good to go. If you had a formula, though, of C5H10, you really couldn't tell, right now anyway, if it was an alkene or a cycloalkane. C5H10 was that 2-pentene thing we saw earlier, all right? It could also be a cyclopentane. So as an organic chemist, you have to be careful. Sometimes you need more than just the formula to figure out exactly what it is, and that's something you'll see a lot in organic chemistry. Let's go back to the cis and trans. In the picture I had earlier, it was trans-butene or trans-2-butene, pentene, excuse me, I think it was. No big deal. These are butenes here. Trans and cis are very important for chemistry and in life in general, as we'll talk about in a little bit. Cis and trans happens when you have a double bond and 2 of the pieces on opposite carbons are the same. And this is a classic example because in butene, you have the hydrogens, which are the same, and you also have on the opposite side the methyl groups. So let me focus on the hydrogens here since I've circled them. In the cis form, the hydrogens are on opposite carbons but the same side, all right? They're both, if you will, facing down. And if you rotated that thing 180, so the methyl groups are on the bottom and the hydrogen groups are on the top, then the hydrogens would both be on the top of the molecule. So opposite carbons, but same side. Trans means that those 2 things that are the same, opposite carbons and opposite sides. So notice how here the hydrogens are like opposite each other. And if you rotated it 90, the hydrogens would be top and bottom instead of bottom and top, but they'd still be opposite, right? So cis and trans, really important. And maybe you've heard about how trans fats are bad for you, all right? A trans fat has a double bond, and I believe they're hydrogens that are trans like that. And trans fats in our bodies don't gel as well with our bodies. They cause cancer. Cis fats apparently are better. So anyway, woohoo, trans fats, cis fats. But anyway, so do cis fats more than trans fats. Anyway, I digress. Cis and trans is really important. The reactivity of a cis is quite different usually than trans. We talked about polarity in chapter 7. Cis is going to be much more polar than trans. The hydrogens are kind of pulling opposite directions from each other, so they kind of cancel out. But in a cis form, you don't have anything canceling for polarity. So cis versions of alkenes are usually more polar than trans forms, so they can be quite different in their reactivity. So just realize that if you have a double bond and 2 things are the same on opposite carbons, you've got to include the cis and trans. If you don't, if you have 3 things that are the same, or if everything's the same, then you don't have to worry about cis-trans. But cis and trans will pop up quite a bit, like we'll see. Cis and trans, to turn a cis into a trans or a trans into a cis is very, very tough. It's a very high energy transition. So you don't usually see cis and trans going through isomerism, which means changing one into the other. It takes a lot of energy to break the double bond, rotate the molecule, and then reform the double bond. It's not impossible, but 240 kilojoules per mole is a lot of energy. You might be more likely to break apart other parts of the the molecule before you broke the double bond. So we don't usually see cis going to trans and trans going to cis. There are some exceptions, but generally speaking, they're pretty permanent and stuck with each other. Both oranges and lemons have different kinds of compounds with double bonds in them. And just the relationship of one to the other makes a really big thing. Oranges and lemons, again, a very similar structure, but one is one way and one is the other way. So you have to be kind of careful. So just knowing about the isomers can be super important when it comes to making different compounds and the importance of alkenes. This leads us into one of the most interesting of the organic chemistry molecules as far as I'm concerned. You can make a cyclic structure, so 6 carbons, if you will, in this case, in like a circle, all right? And you can have alternating double single, double single, double single bonds. So it's kind of like a cycloalkane, but it's with an alkene, and there is a type of a family of compounds called cycloalkenes. However, in the right combination, and this one is an example of that, those alternating double single bonds create a type of a ring current because resonance allows the double bonds to trade places, like they all rotate by one bond. And the resonance like goes on and on. So they rotate by one, then they rotate by a second, then they rotate by a third, and they go on and on and on. So sometimes you'll see this type of structure written as 6 carbons with just a circle in the middle of it. And the circle is basically a way to represent the resonance of it. So sometimes those double bonds, when they're conjugated, which means alternating double single bonds, you get an increased stability. And if you end up with this kind of combination, you have what's called an aromatic hydrocarbon. And aromatic compounds are especially stable, and they have real special kinds of reactivity. This is a really interesting, in my opinion, part of organic chemistry. There's a lot of information that we're not going to talk about in relationship to aromatic compounds, but we're going to talk about the simplest of the aromatic compounds, which is called benzene. And benzene is literally 6 carbons in a circle. You have alternating double single bonds. They will resonate, they will rotate around each other, and you end up with this wild kind of ring current. You can see that the molecule is flat, and the flatness does create some special reactivities. Like some of the reactivity that you expect for an alkene doesn't happen with an aromatic compound. And sometimes aromatic compounds will react in ways that the alkenes won't. It's a real interesting kind of phenomenon. These pictures here show the different types of electronic networks. The upper left one is just the sigma bonds, all right? And again, sigma is the head-to-head overlap between carbons and stuff like that. The lower left one shows the pi bonds. And again, back to our discussion from the last chapter, pi bonds are kind of like the bread of a sandwich, and the sigma bonds are kind of like the quote-unquote meat that goes in the middle. And then the upper right-hand picture shows the bread and the sandwich all together. It's making me hungry. I shouldn't have talked about it. Anyway, Prophet back on. So the sigma bonds are cool, but it's the pi bonds which are really interesting here. You would expect with a regular double bond system, you would just have a little bit of pi bonds like here and there, like alternating, but they don't. They resonate like crazy. So it creates that kind of donut looking thing, which is literally the pi bond kind of running around and around and around in a circle. And they've measured these kind of ring currents in the molecules, which are very, very interesting. But the ring current does create a special kind of stability and reactivity that you don't see in other molecules. So basically it's the pi bonds, those pi electrons, that create the aromatic stability, which is really cool. In organic chemistry, this is a fascinating area of research, I think. A carbon-carbon single bond is about 154 picometers, and a carbon-carbon double bond is about 134 picometers. So remembering how as bond order goes up, the bond length goes down. So bond order 1, carbon-carbon single, and bond order 2, carbon-carbon double, you can see how bond lengths are certainly decreasing. Well, in benzene, the carbon-carbon bond length's 139 picometers. Now, technically, we would think think of the carbon-carbon bond order as not 2 or 1, but kind of a hybrid, because these are resonating around. So instead of having doubles and singles, you would expect the bond order to be about 1.5, more than a single bond, less than a double bond. However, because 139 picometers is pretty close to 134 picometers, there's something else going on here. All right, the resonance in an aromatic compound is like an extra level of stability, making it a little bit stronger. So this delocalized pi network is very, very cool, and that's a direct result of the resonance in aromatic compounds. You can place different pieces on a benzene ring, and they have some special names. We're going to talk about these more in lecture and also in the organic chemistry lab. If you put a methyl group on a benzene ring, the official name for that would be methylbenzene. However, nobody calls it methylbenzene except for nerdy chemists. Toluene is the name that's usually used. So toluene is just methylbenzene. All right, it's like a common name. Toluene is something that you can buy at Fred Meyer's or Home Depot. It's a lot of times used for taking paint off things and stuff like that. Pretty interesting. In the upper left corner, we have an ethylbenzene, which is just an ethyl group connected to a benzene ring. Nitrobenzene is an NO2 connected to benzene. Bromobenzene. In the upper right-hand corner, an alcohol connected to a benzene ring is called a phenol, and that's something that's kind of cool. Benzoic acid, we'll talk about more in Chem 223. Benzoic acid is a COOH. We'll talk about that more here in a little bit, but benzoic acid. And finally, you can have multiple benzene rings connected to each other. Naphthalene is 2 benzene rings connected to each other. So you have actually 2 rings in those guys. It's really cool. Naphthalene has all kinds of different possibilities. So there's lots of examples of these aromatics and stuff we'll see. If 2 of the positions around the benzene ring have the same kind of substituent, there's a special kind of a naming that's used. And the old way of calling them is by ortho, meta, and para. So what we're seeing here in these examples are a series of dichlorobenzene groups. And in the example on the left, the chlorines are right next to each other. In the middle, there's a spot between them. And in the one on the right, they're opposite. If they're right next to each other, like the first one, then the official name would be 1,2-dichlorobenzene. But you will still see it listed a lot as ortho-dichlorobenzene, or what they usually use is just O-dichlorobenzene. So ortho means 1, 2. I prefer the numbers personally, but ortho, meta, and para you'll see a lot too. Meta means 1, 3. So 1,3-dichlorobenzene is also called meta or M-dichlorobenzene. And para means 1, 4. So 1,4-dichlorobenzene is the same as P-dichlorobenzene. And you could have dibromos, diiodos, dimethyls, all of those things, ortho, meta, para. Again, I prefer the numbers, but you will see the letters as well. Either way is fine. Carboxylic acids have the generic formula with a COOH connected to some kind of alkyl group. And COOH consists of a carbonyl, a C double bond O, connected to an OH group. So it's like a carbonyl with an alcohol next to it, and then there'll be some type of alkyl thing to the other side. This is a special kind of a reactivity. The hydrogen on the end of the OH is actually slightly acidic. That's why it's an acid. Carboxylic acids are all weak acids. They're not very strong, all right? But they are really important. A lot of them are in common things around us. An example that's rotating right there, there are 3 carbons, and it's a carboxylic acid because it has a C double bond O and the OH on the end. If it was an alkane, it would be propane, but because it's a carboxylic acid, you take off the E and add oic acid, propanoic acid. The carbon number 1 is always the carboxylic acid. So the carbon with the oxygen and the OH on it, that would be number 1, 2, 3, etc., etc. Formic acid is the simplest carboxylic acid where you have just a hydrogen next to the COOH. Formic acid is another type of carboxylic acid. Acetic acid is a compound we've run into here and there, and it's related to the acetate polyatomic ion. And maybe now you can see why it's listed as so many ways. Acetic acid is a common name for ethanoic acid. Ethanoic acid means 2 carbons, and those are the 2 carbons right there. And those 2 carbons, there's a C double bond O. This is the double bond O, and the OH. So instead of calling it ethanoic acid, most people will call it acetic acid, which is fine, whatever. But anyway, because it's acidic, the hydrogen on the end right there will a lot of times pop off. And if you look at the rest of that molecule, you've got a CH3 followed by a CO2. So acetate and acetic acid are related to each other. Acetate is CH3CO2 -1, and acetic acid has a hydrogen on the end of it. So this is the joy, and this is why the acetate ion is so weird to talk about. Like, do you write it CH3CO2 minus? Do you call it C2H3O2 -1? There's a whole bunch of different ways to write acetate, and now you can understand some of the confusion around it. Now, benzoic acid on the right is a benzene ring, C6H6, but one of the hydrogens was pulled off, and you're putting that C double bond OOH off of it. And again, like acetic acid, that hydrogen is acidic. It pops off. It makes what's called the benzoate ion. We'll talk about that more in Chem 223. But again, the important part here is that all these carboxylic acids, that hydrogen next to the O is slightly acidic. When the hydrogen as H plus plops off, you have an O -1, and the double bond O, it'll resonate back and forth. So the O -1 can kind of go back and forth between the oxygens. It provides a little bit of stability. And the same thing with acetic acid. These acids are found in lots of natural substances. A lot of the things we eat actually have slightly acidic parts. Our bodies are used to things that are a little bit acidic. Vinegar is actually basically just acetic acid. All right, they'll put other kinds of spices and stuff in it to give it different flavors, but basically the ingredient of vinegar is just acetic acid. It's a pretty dilute acetic acid. You can buy much more concentrated ones in a chemistry lab, but it's still kind of cool. Yeah, put some acetic acid on your salad, i.e. some vinegar. Okay, getting too excited here. Formic acid is, again, the simplest of ones. If you've ever been stung by an ant, that's what they use to make the sting part. So it's pretty powerful stuff. Aspirin is another type of a weak acid. The part right up there has a little bit of an OH on it. Acetylsalicylic acid is the technical name for it, which you'll learn more about in organic chemistry. Notice that down here we've got a C double bond OO, but it's not an acid. That's another kind of a compound with a benzene ring in the middle. So you can see how this stuff can get pretty crazy. But again, we're just putting our, big toe in the water here, getting a feel for what it's like. And then in the actual organic chemistry class, you'll be able to rock this stuff. Let's name this compound, all right? And again, longest chain, smallest number, identify the family, all that kind of stuff. All right, so by this time you can probably see we got to count the number of carbons. There are 1, 2, 3, 4, 5 carbons, all right? So it's going to be pent something. So answer A is flat out. This thing has a carbonyl, a C double bond O, so it might be tempting to think it's a ketone or something, but it's not. This carbonyl has an OH next to it. So it's not an alcohol, doesn't have an OL ending. It's not a ketone, ONE. It's not an aldehyde, AL. If you have a carbonyl, a C double bond O next to an OH, this is a carboxylic acid. And because there are 5 carbons next to it, this is going to be called pentanoic acid. 5 carbons, carboxylic acid, you're good to go. Butanoic acid would have only 4 carbons, not 5 total. The carbon with the carbonyl, the carboxylic acid group does count, by the way. Pretty chill. The last family of compounds that I want you to know for Chem 222 is what they call an amine. And while a carboxylic acid is a weak acid, an amine is the equivalent but weak base. And acids and bases, sometimes we use them for energy sources, so amines are also really important. Amines have a nitrogen. This is the first time we've seen nitrogen in these compounds. The nitrogens here are sp3 tetrahedral, but the nitrogens do have a lone pair on them, and I want you to remember that. So because of the lone pair on the nitrogen, there are 3 spots left. You can have all 3 spots as alkyl groups, R. You could also have all 3 as hydrogens. If you have all 3 as hydrogens, then in that generic formula, X is 3, and R, 3 minus 3 would be 0. You wouldn't have any alkyl groups. On the other hand, you can have all the groups alkyl, so you'd have 0 for X, you'd have 3 alkyl groups off a nitrogen, etc., etc. Naming these for us is not usually too bad. If you have an ethyl group connected to a nitrogen and 2 other hydrogens, this becomes ethylamine. So the CH3CH2 is the ethyl group. It's connected to the nitrogen, which is an amine. No problem. Now, this is a single ethyl. You could also have a diethylamine. So if you took off one of the hydrogens in H2 there, you could have 2 ethyl groups, a nitrogen, and 1 hydrogen for diethylamine. But you could take all the hydrogens off, put 3 ethyl groups next to the nitrogen, you'd have triethylamine. So you can hopefully see how this stuff kind of works out. So let's name this compound, all right? And you can see there that there are 2 methyl groups, 2 CH3s. They're connected to a nitrogen with 1 hydrogen. So things connected to a nitrogen are amines. The methyl group, there's 2 of them, so it's dimethyl, all right? It's going to be dimethyl something. If you look through this list here, that some of them are kind of funny sounding, but dimethyl nitro, that doesn't make any sense. Dinitrane sounds cool, but that doesn't make any sense either. This one is definitely going to be dimethylamine, 2 methyl groups off the nitrogen. And of course, you could have trimethylamine, which would be 3 methyls and no hydrogens. If you have all hydrogens, that's ammonia, NH3, which is the simplest one. The other answer is methylated nitrane doesn't make any sense, and Drano is essentially sodium hydroxide. That doesn't count either. So here's the methylamine, dimethylamine, and trimethylamine list of families. And again, the blue atom there is the nitrogen, and on top you're going to have a lone pair. So like carbon, nitrogen wants to have 4 groups around it, so you're going to have 3 positions for connections to atoms. And as you take off the hydrogens and add methyl groups, you can see in the last one they're all gone, but you still have that lone pair on it. Amines generally have really bad smells, and boy, oh boy, like ammonia has kind of a powerful smell, like in smelling salts, but the other amines, in my opinion, are just horrible sounding, and they're really funky. But anyway, cadaverine smells like a cadaver. That's actually a diamine. There's 2 amine groups on it. And pyridine, man, that stuff is really funky. This is kind of strange, but Viagra has a certain effect on men. Pyridine would be the anti-Viagra. It does the opposite thing. So pyridine is one I always tried to stay away from because, well, I'm a human being and I'm male and I don't want to have the anti-Viagra effect happen on me, shall we say. So be careful, people, if you're around pyridine. I would, anyway, it's a long story. You've been warned. All right, just say no, whatever. I want to introduce 2 families of organic chemicals, but I don't expect you to know what they are. And those are esters and another one coming up called an amide. Esters sound a lot like ethers, but they're quite different, all right? An ester is when you have a COO, a carbonyl with a single oxygen, but instead of having a hydrogen like we saw in an carboxylic acid, you have another alkyl group. So these are named kind of strange. They usually have the 8 ending, like you can see right there. An ester, again, is not one that we're going to talk about a lot in Chem 222, and you don't need to memorize, figure out how these work. But I want you to hear the name because an ester is different than an ether. And I got kind of jammed up on a quiz over this, so maybe that's my reason. Anyway, that compound there in the lower left, the ethyl group is smaller than the 4-carbon group on the left, a butyl group. So the ethyl, which is to the other side of the single bond oxygen, followed by butyrate would be the way to name it. We're not going to name these. If you see the ATE ending, a lot of times in organic chemistry, that means you've got an ester. Just realize they're out there. They've got wild reactivity, which is something you'll talk about in the organic chemistry class. The other group I want you to hear about is called an amide. An amide is different than an amine. And again, this is something else that got me on a quiz one day. But anyway, I digress. An amide does have a nitrogen, like an amine, but the nitrogen is connected to a carbonyl. So you've got a carbonyl, C double bond O, connected to a nitrogen, and you have potential for alkyl groups on both sides. A lot of times with amides, you'll see that capital N. So N-methylpropanamide means that you have a methyl group connected to the nitrogen, so that the N has a methyl group on it, and because it's an amide, instead of propyl, you call it propanamide. This is another really cool group. There's a lot of neat uses for amides, but again, that's more than we need to get into in Chem 222. So just realize amide is different than an amine, just like an ester is different than an ether.
To visually reinforce the fact that members of a homologous series, such as we see here, differ from each other by a specific structural unit, we use molecular models. Here, for instance, is the tetrahedron of carbon, a model of methane. In order to turn that model into ethane, we add another CH3 group to the end by substituting for a hydrogen. If we wanted to go from a propane to an ethane, we would remove that specific member of the homologous series, a CH2 group. Reconnecting the carbon atoms, then we're back to our ethane. Models can be used that are commercially available, but if they're not available, gumdrops work just as well.
If you are planning on taking the year-long organic chemistry course after the Chem 221 through Chem 223 series, I really highly recommend to the strongest degree possible that you buy a model kit. You're going to see that there's so many changes that happen with the geometry, and we haven't talked about all the types of isomers that are possible in organic chemistry, but having a model kit is really important. A good model kit will do not just single bonds, but also double bonds, so you can see cis and trans. They'll do triple bonds and all kinds of cool things. So again, if you're going to take organic chemistry, the year-long class, you really, really need a model kit. You can use gumdrops, absolutely. All right, little gumdrops and little toothpicks and stuff. However, my problem was I was studying, trying to use gumdrops, and I'd start eating all the gumdrops. Gummy bears work as well, but again, those went down as easily as gumdrops. So I didn't eat my model kit. That's what helped me. But anyway, that's my personal problem and not yours. But anyway, if you take OChem, you should absolutely get a model kit. They're pretty cool. The other big part of organic chemistry is how the chemicals react. And this is by far the bigger portion of organic chemistry relative to nomenclature. Knowing how to name things is definitely the first step. But the reactivity is just crazy because you have to know what to do with the chemicals when you have them and how to make them if you don't have them. So we're just going to look a little bit at some general patterns, all right? And in the actual organic chemistry class, then you'll start seeing more examples and you can get into more detail. So kind of bear with me here while we go through some typical examples of how organic chemistry works. An addition reaction is what happens when you have an unsaturated alkene and you add a diatomic molecule to it. And the double bond breaks and you end up with single bonds. So here's an example of what this means. A double bond, or a triple bond for that matter, is considered unsaturated, which means that you have more spots that you can put atoms if you break apart the double bond. Like you can break apart some of the carbon-carbon bonds. So if you add bromine, for example, then one bromine atom goes to the left carbon and one to the right. You can see how they basically separate and go where the double bond was. So your ethene compound on the left reacts with bromine to make 1,2-dibromoethane, which is an alkyl halide. Now, if you added hydrogen, H2, to the ethene, you would turn it into just ethane. You're turning an alkene to an alkane. If it was HBr, then one hydrogen would go to the left and one bromine would go to the right. So you'd end up with something like 1-bromoethane. You could add water. You'd have an H and an OH. It's pretty cool. Those double bonds are actually pretty reactive, and adding a diatomic to it means you can break it up.
Molecules of bromine gas undergo an addition reaction with the carbon-carbon double bonds in bacon fat, causing consumption of the bromine gas.
This is an example of adding bromine to a double bond and then breaking it up to make a dibromo. This is bacon fat, which is pretty disgusting. But anyway, you can break apart the fat in the bacon and the bromine is used up. Bromine has that kind of dark yellow kind of looking color when it's in the gas form, and then as it reacts, it does different things. So, oh joy, the fun you can have with chemistry.
Atoms of hydrogen gas undergo an addition reaction with the carbon-carbon double bonds of propene, changing the molecule into propane.
You can easily turn alkenes into alkanes by adding just hydrogen. So this was turning propene to propane, all right, which is really simple. Like I've kind of mentioned earlier quickly, an alkene is much more reactive than an alkane. Alkanes usually are just good fuels, more or less, but alkenes, you can do lots of things. You can add diatomics across them, stuff like that. Fats can be hydrogenated with hydrogen, H2, all right? And sometimes that's good. It makes them easier to store or not quite as readily to break down, stuff like that. And this leads into hydrogenated fats. And if you look on the sides of some containers, you end up with partially hydrogenated oils, all right? That means that hydrogen was added. They're trying to break apart the unsaturated fats into saturated fats, and there's reasons why they want to store it. A lot of times, though, the partially hydrogenated fats are really bad for us, and so you should be careful of them. But anyway, this is the process. They're trying to add enough hydrogen to make the double bonds break up into single bonds. I am reluctant to think that any of these processes are 100%. So I would be very, very careful if you were going to consume hydrogenated oils. I don't think that they're totally free of some of the bad things in them, but that's my personal theory.
In the substitution reaction of glycerol with nitric acid, hydrogen atoms on the glycerol are replaced by the nitro group to produce nitroglycerin and water.
Nitroglycerin is essentially triol glycerin with a nitro group, and if you add nitric acid to it, it'll make it. It's pretty unstable, causes lots of cool explosives. This is an example of a substitution reaction where you're taking some more exciting pieces and basically swapping them out. So the NO2 basically swaps out one of the hydrogens on one of the OHs, so you end up with this nitro group, and again, that's pretty unstable. There's a lot to substitution reactions, and again, in the organic chemistry year-long course, you'll go into a lot more about substitution reactions.
In the reaction of 1-propanol and sulfuric acid, a hydroxyl fragment is eliminated from the 1-propanol to form propene.
Earlier I said how alcohols are also very reactive, and this is an example of what this is. If you have an alcohol and you accidentally or intentionally add a little bit of acid to it, acids act as a catalyst, so it means they react with a chemical, but they're also regenerated at the end, so they can react more. But anyway, the acid will actually cause water to be kicked out of the alcohol, and an alkene forms in its place. So you're essentially turning then these kind of alcohols into alkenes, which is kind of cool and stuff, but it is pretty interesting. When we ship our waste, we have to make sure that they are certainly not acidic, because a lot of times with organic chemicals, you can make wild reactions happen. This is called an elimination reaction. You're essentially eliminating the OH of the alcohol and another hydrogen to the adjacent carbon to make the double bond. And again, you have to have H plus as a catalyst to get this started. We'll talk more about catalysts towards the end of Chem 222. Another subject which is not discussed enough is what's called polymers. And polymers are just giant, usually organic molecules, which are made by joining many smaller pieces together. And the smaller pieces are called monomers. So a monomer would be like one piece. Polymer means many pieces coming together. And the reason why this is so important is that if you look around you right now, I'll just about guarantee you're going to see plastic, all right? Maybe it's on your computer or in your phone, or maybe you're using a pen or something like that. Roughly speaking, every year, 150 kilograms of polymer is made per person in the United States. And I mean, that's a lot, all right? And, it ends up in landfills and people try and recycle it and stuff like that. And that's a whole nother discussion. But there's a lot of polymer made per person. So it's important to talk about a little bit anyway about what polymers are. So we're just going to have, again, a real brief overview of polymers, which is another arguable subset of organic chemistry that a lot of times people don't talk about. So polymer literally means many parts put together. In the lower right-hand corner is a quote-unquote formula for polyethylene. So in the brackets there, you can see there's a CH2, but then there's a line going through, and on the bottom there's an N. So in this point, that's the ethylene monomer, the individual piece, and it goes together N times to make a long chain of these CH2 parts. So you'd have CH2 and another CH2, etc., etc. So polyethylene, many CH2s. Now, the ends could have a whole bunch of different stuff on them, but if you have like 100,000 monomers and something weird on the outside, who cares what's on the outside? The chemistry of that molecule will be like the monomer piece, and that's why people focus on the monomer parts more than the whole thing. So many mers or monomers pieces or units will combine to make a polymer, many pieces altogether. These things have incredibly high molar masses. 1,000,000 grams per mole is not unheard of by any means. And again, a lot of things around us are polymers. A lot of fabrics, Teflon if you use nonstick pans and stuff like that, and many more examples. You can synthesize polymers through addition or condensation reactions, and I want to briefly talk about them. We're not going to go into either one of them in a lot of detail, but I think it's important to know in case you end up working for them or you want to know more about polymers and the effect they have on society.
Addition polymerization begins when an organic peroxide produces free radicals. These can react with a monomer to produce another free radical. This unstable intermediate can react with a second monomer to form a larger species. Eventually, a polymer chain grows. The chain can grow to contain many thousands of monomer units. A termination step seals the reactive end of the growing chain. One possible termination is the coupling of two chains.
This is an example of an addition polymerization reaction. And what they do a lot of times is they'll take a peroxide. So like hydrogen peroxide was HOOH. You can have organic peroxides as well with an alkyl group on both sides. But that oxygen-oxygen single bond is actually quite reactive. And you can break it apart into two paramagnetic little centers. So the oxygen has an odd electron. And like we've seen a lot, odd electrons are super reactive, and they will combine with the pi electrons in ethene, carbon-carbon double bond, and it basically extends the paramagnetic part to the opposite side. And that paramagnetic part reacts with another ethene to extend it even further, and then finally you have some kind of termination step where the two paramagnetic ends basically come together, and you can have just incredibly long chains of molecules. So for example, if you have a molar mass of about 1,000,000, that million grams per mole, that would be about 360,000 of these little CH2 units. And again, those pieces on the end are not going to be that important to the chemist. It's the reactivity will be displaced by the CH2 going on and on and on, which is pretty interesting. Here's an example of how to make polyethylene. In this example, which is what I saw online, they're using a compound called benzyl peroxide, and it's that OO single bond in the middle, which is important, and it's pretty unstable. So you actually heat it up and you break it apart into two paramagnetic pieces. So you can see right there, there's a little odd electron. That's super reactive. And if that little piece comes into contact with something like a double bond, the double bond is broken up. One electron goes towards the oxygen, making a single bond, but the other electron then is paramagnetic unto itself. So you end up with a benzoyl radical, which is basically a paramagnetic thing now with the carbon having the paramagnetic piece instead of the oxygen. And then that just keeps growing and growing and growing. So you keep adding more and more. So you can see on the left-hand side there were N units, and on the right-hand side N+1 keeps growing and growing and growing until finally you get to a termination step where two paramagnetic pieces come together. This is reacting with another benzoyl radical, but it could be another long line of carbons, whatever. It becomes diamagnetic, and diamagnetic things are more stable, so it kind of stops the reaction. So when the two radicals come together, you'll see it. You will end up with a different breach of compounds. You'll have different molar masses, but usually you've got some kind of overall molar mass, and they react pretty close to each other, so they can be useful. Linear high-density polyethylene is HDPE. You may have heard that. That's basically like a long line of these carbons just in a row. There's no branching or anything like that going on. But you can also end up with branched systems, all right? There's low density, there's cross-linked and stuff like that. There's actually a lot of really cool science when it comes to ethylene. And again, a lot of these can be recycled, which is nice when you make 150 kilograms per person per year. But anyway, just something to think about as we go through as scientists and human beings. If you take polystyrene and you place it in a solvent like acetone, it actually shrinks way down. Polystyrene foam, which is used in peanuts and stuff like that, is mostly air. And if you can dissolve it, then it collapses, so the volume just goes way down. So that beaker on the right is the same number of peanuts as you see on the left, but now they've dissolved in the acetone, so make them. It's kind of a fun little nerdy trick to do. Another type of way to make polymers is through a condensation polymerization reaction. And again, this is a little bit more sophisticated kind of reaction, but there's a lot of real practical uses for it. You basically take different functional groups and you make polymers that have quite different properties. So like the polyethylene, basically all of that is CH2. It all reacts the same. In a condensation reaction, you can actually have different parts with different properties, like more polar, less polar, maybe acidic, or something like that. Pretty cool uses. If you've ever worn contact lenses, you have definitely used the result of condensation and polymerization reactions. Nylon is also a function of this kind of stuff, so there's some cool uses for it.
Ethylene glycol and terephthalic acid can react with each other at both ends of either molecule. The reaction produces a molecule of water and allows the bonding of the remaining molecules. If many such molecules are available to react, a polymer chain of polyester is produced.
In this example, which is how they make polyester, they're basically taking a diol, a compound with two alcohol OH groups, and another one which is a dicarboxylic acid, C double bond OOH on both sides. And then A and B just represent the chemicals that are in between, but A and B are definitely different. And as they combine, you can see that water is kicked out. So scientists will sometimes measure the amount of water released to see how they've done, and you end up then with some cool kind of properties. Here's what the actual A and B kind of parts looks like. So terephthalic acid there on the left is basically a benzene ring in the middle of carboxylic acids. And ethylene glycol is basically CH2CH2. That's the part in the middle of that diol. And then when you combine them, you end up making polyethylene terephthalate, PET, which is a polyester. Phthalates have been in trouble recently because of how things they do in the body. They're used in a lot of water containers. This is a type of a phthalate and stuff like that. There are types. Some people say that some of them are safe. Some people say they're all bad. I'll let you decide that on your own. But at least this is how you can make these if you wish. Jackets can be made from recycled PET soda bottles, which is really cool. There's lots of different uses for it. Balloons, a lot of times, are made from these kind of things, and soda bottles. Lots of cool uses for polyesters.
When adipoyl chloride and hexamethylene diamine come into contact, hydrogen chloride is given off and a polymer is formed. This polymer is commonly known as nylon 6,6, one form of nylon. The number 6,6 indicates that there are 6 carbon atoms in each of the monomers.
This stuff is really fantastic. You can see how the chemicals formed at the interface between the two chemicals, and then they kind of pull it out. This is the example of what happens in this compound, nylon 6,6. It's the interface of the two. And again, these things go on, so they have lots of uses, stuff like that. Nylon is, again, a possibility. That was nylon 66. This is the actual chemicals that are involved. There's a numbering system why it's 6,6. It has to do with the number of carbon atoms in the two parts, the A and the B, that come together. That's kind of beyond where we are right now. In this particular reaction, HCl is given off instead of H2O. So you can also measure how much HCl is coming off, either through titration or through some kind of direct measuring technique. Lots of uses for polymers. Teflon is one that's been used in non-stick containers for cooking. Of course, fabric is one we talked about a little bit. Milk and soda bottles is a big-time high-density polyethylene, so if you drink a pop or something like that, you'll see it. Styrofoam, of course, used for lots of things for cooking. Plastic wrap, saran, contact lenses and stuff, definitely. One of my favorite uses, bubblegum. Bubblegum is actually a copolymer, the basic ingredient between styrene and butadiene, and of course they put different flavors in it. I wouldn't recommend swallowing your gum, but if you do, it's probably okay because I think it's pretty inert. On the other hand, if you can spit it out in a garbage can, probably better for you. Slime is another one. If you ever played with this kind of stuff, you can make your own slime. It's a cross-linked polymer with boric acid, kind of fun stuff. Anyway, I'm still a child at heart, of course. Recycling, so important, and this is again where a little bit of my personal feelings come out, so if you want to fast forward, it's all right. But so much polymer is created per person in the United States that we'll just start swimming in it pretty soon. And people talking about microplastics in the ocean, which are just horrible. So I certainly recommend that you at least try to recycle things. And some of them are easier to recycle than others. There's a numbering system, 1 through 6, and 1 through 6 each actually represents a specific polymer. So you can see like number 6 there is polystyrene, and number 1, polyethylene terephthalate, etc. Number 7 is the one they usually don't know what to do with, although some recycling measures will take all the plastic, so it doesn't matter. They can separate them out by density. Those are the relative densities of the different polymers and stuff, so you can separate them out various ways. Try to recycle if you can. That's my only thing I'm going to say. Okay, that's the end of the organic chemistry section, stuff like that. I really appreciate you spending your time with me. I definitely recommend you check out both the study guide and the concept guide for these chapters. The study guide is a bulleted list of the important parts. Concept guide actually shows some worked examples. So especially on nomenclature and stuff, that can be kind of important. After this, there will be some important equations, which is more about naming in this section. There's not a lot of math. And then also after that, there will be some end of chapter problems. So it'll show some questions followed by answer. I definitely recommend you check those out. Make sure you've got it. If you do get stuck in any of this material, don't feel like you have to live in a bubble. You're welcome to reach out to me. Email is awesome. You can also reach out to the Learning Success Center /Avid Center at Mount Hood, and they will help you out as well. All right. Good luck with your studying and have a wonderful day.